Good morning, everyone. Welcome to the lab session number 3, Discharge over Weirs. So for this lab session, we will also have the lab number 3 slides, these slides, and the lab number 3 group data sheets. So we will have that information along with the recorded experiment videos and along with this recording to be able to do the report. So, discharge over Weirs. So in an open channel, flow rate can be measured similarly by introducing an obstruction into the flow. A simple obstruction called a weir consists of a vertical plate extending the entire width of the channel. So the plate might have an opening, usually rectangular, trapezoidal, or triangular. So imagine this. Imagine you have a river. Imagine you are seeing a river and you are wondering what is the flow rate the river is going through and at what velocity. And since we don't have the cross-section area, if we have a river, we cannot find the cross-section area of the river because it varies along the way. So we can create a weir with a known cross-section area to calculate the parameters of the flow. If we create a rectangular weir, we will force all the flow to go into that rectangular section, and then we can calculate an h and therefore calculate the velocity, flow rate, etc. So for the equipment in this experiment, we will be using the open channel flow apparatus and several weirs. And there are two types of experiments. We will use a rectangular weir and a V-notch weir. So the scope of the experiment to derive the relationships between head and discharge. These will be the two important parameters we will be obtaining in this lab. So this is the open channel flow apparatus. You can see that the weirs, we have the plates for the weirs, and basically the flow, basically this instrument is connected to a hydraulic bench, which the hydraulic bench is located at the bottom of this equipment. And what happens is that we will have a hose in here, which flow will enter through this direction. It will fill this left part of the tank, and the flow will go in this direction. So when it finds the weir, then all the flow will go inside of the weir, and then it will discharge into the other part of the tank and discharge into the hydraulic bench, and then it will recirculate. So the hydraulic bench has a pump underneath, so it basically recirculates the flow. Yeah, water is distributed evenly in the large tank. In this one, that leads to a short channel at the end of which there is a sealed groove where the weirs are attached. In this part, and the water after reach the weir then flows over and then is collected to the exit tank, which is this one. In order to measure the head of the water in this case before the weir, that is to say upstream, we will have a point gauge which is this instrument in which we will calculate the head of the flow. So there is a little bit more close-up of the weir in question. So this is the h we will be looking for in the experiment. So we have a weir, and for example, if we have a weir without a flow rate, our water will stay in this level. So when we start having a flow rate, the water will start going, and then it will create this h, which is the delta h. Usually the head of the weir it's 2 or 3 times the h of the head of the flow generated by the flow rate. Also, there are types of weir. There are rectangular weirs, or there are trapezoidal weirs with an inclination of 45 degrees. And here are the rectangular weir with end contractions and the V-notch weir. So this is a frontal weir, a view of the weir, in which our cross-section area will be this area for the rectangular weir, and our cross-section area for the V-notch weir will be this area. So in our case, we will use a rectangular weir and we will use a 90-degree V-notch weir. That is to say that this angle, this angle is 90 degrees. There are smaller weirs that with an opening of 30 degrees, but in this case we will use a weir with 90 degrees of opening. So the apparatus allows for the insertion of a weir and the measurement of liquid depth, this H, like I said. The following figure is a sketch of the side and upstream view of a 60-degree V-notch weir. Note that upstream measurements are made from the lowest point of the weir over which liquid flows. So our base measurement we need to take in the experiment is that we need to know this head, and then which will work as a base. So for example, we have our weir, and we need to calculate the head of the base of the weir to have a base H. So we will calculate this H, and then we will turn on our pump, and then we will generate flow. Is that to say that when we generate flow, we will create a different H, so then we will calculate this H. And the difference between these two measurements, it will be our delta H. Note that upstream measurements are made from the lowest point of the weir over which the liquid flows. Yeah, like I said, our goal is to calculate this delta H. A little bit of the theory of flow over sharp-edged weirs. A coordinate system is imposed whose origin at the intersection of the free surface and a vertical line extending upward from the vertex of the V-notch. We select an element that is dy thick and extends the entire width of the flow cross-section. So going back, we will select this dy that extends the whole cross-section area of the weir. This is the cross-section area we will be using to theoretically obtain the equation. The velocity of the liquid through this element is found by applying Bernoulli's equation. So we have here Bernoulli's equation. In open channel flows, the pressure terms represents atmospheric pressure, since we are doing at an atmospheric level, and cancel from the Bernoulli's equation. That is to say that these elements of the equation will be zero. Also, the liquid height is therefore the only measurement required here, from the above equation assuming BO negligible. So since we are assuming that at the starting of our experiment the velocity will be zero, we can assume that this is zero as well. And then having these three parameters, we can obtain that the velocity is the square root of 2gy. So the incremental flow rate of liquid through a layer dy is the square root of 2gy 2x dy. From the geometry of the V-notch and with respect to the coordinate x's, from the V-notch weir of angle of 2 theta, where theta is the angle of vertical, the width of the system is 2h minus y tangent of theta. Thus, the flow rate integration as above is equal to. So this is the integration when for a B-notch weir with an angle of 2 theta. Like I said before, we have different angles for our weirs. In this case, our angle of our weir is 90 degrees, but the 90 degrees equals to 2 theta. So the theta in this case will be 90 degrees divided by 2, because we are considering just half of the angle. So this is theta. So it will be equal to 45 degrees in the calculations. Remember that the whole opening of the weir, it represents 2 theta. So after obtaining the integration, it will give us that the flow rate equals to 8/15 of square root of 2g sorry, multiplied by tangent of theta multiplied by a head. In this case will be our delta h, our head to the power of 5/2. It is therefore customary to rewrite the equations in the form of flow rate equals to CD multiplied by 8/15 to square root of 2g tangent of theta multiplied by h to the power of 5/2 for the B-notch weir. And also we have a customary equation for the rectangular weir, which is the flow rate equals to CD multiplied by 2/3 multiplied by square root of 2g multiplied by b, which is the base of the weir. So for the rectangular weir, we have our weir, and this will be our base, multiplied by h to the power of 3/2. So like I said, our h will be this. And the same way for the V-notch weir, our h will be this, and our theta will be half of the angle of the total angle of the total opening. So you can see that for these two equations we have this new term CD, where CD is inserted as an experimentally determined coefficient that includes the effects of the phenomena disregarded in the previously simplified equation. So this equation without the CD means that our flow will be ideal. That is to say that, as I said in the last class, that we don't have any kind of obstruction, we don't have any kind of roughness, or we don't have any kind of viscosity in our flow. It will be considered an ideal flow. So this CD represents all the roughness or all the phenomena disregarded in the previously simplified equations. So since we can calculate our flow rate, then we can also try to find a way how to calculate the CD. So a way to calculate the CD is to find and the exponent of h is either of the flow equation solved above as it follows. So we have this new equation, Q equals to K multiplied by h to the power of n. And this equation we can transform it if we multiply by logs. We can we transform it and we create a log of Q equals to log of K. Remember when we have a multiplication in the logs becomes a sum. So log of Q equals to log K plus n log of h. So if we have a term with in terms of a power, it will go in this way. So this is the equation that we obtain from the simplified equation. So we have to find a way to represent this equation in this equation also. So we can, as you can see here, this is our equation for the rectangular weir. So we really want to relate these two equations. So we can also apply the log in this equation, and we can have log of Q equals to, remember the CD is constant, also the 2/3 and also the 2g, because the gravity is known. So all these all these equations are constant. All these parameters are constant, sorry. So we can do log q, and we can consider as one this term. So we can also do log of CD multiplied by 2/3 multiplied by square root of 2g multiplied by b plus log h to the power of 3/3. And then we will have log of q equals to log of all these plus 1.5 h, since we transfer this power into this way. So we have this equation of logs also, and you can see all these. So you can see these two equations are extremely similar. So in this case, you have our log q, our log of this term will be k, and n will be 1.5, and log of h, I'm sorry, okay, here is log h, and then we will have this equation the same way to this equation. So so in this term we can say that k will be equal to cd multiplied 2/3 multiplied by square root of 2g multiplied by b. So we can determine that k is this equation. So this equation is extremely important in order to find CD. So when, for example, in your experiments, you will calculate a velocity. Sorry, you will calculate an h, and you will calculate also a flow rate with the hydraulic bench. So you can, so for example, you have the x and y axis in here, and you have your points in here. This is another measurement. This is another measurement. You have these measurements. So you can transform your measurements of h and q. You can rewrite into the coordinate system as log h and as a log q. So if you do this, then you can easily find the regression equation in Excel for this data sheet for these data sets. So you will have your equation, and then you have your linear equation, which is y equals to mx plus b. And this equation you can easily transform into, or you can easily relate into this equation, and then you can easily also relate to this equation. So for example, in short, you have your y equals to mx plus b. The b in this case will be k, since the b is the constant. The mx is the m is the slope, which in this case is n. So let me write here. The m will be n, which is the slope. The b will be equal to k in this case, which is the constant, and y will be equal to log q, which is the y-axis. So this is the way you need to find out the k. You have a k with your experimental data, which, because it will be b, you have the k, you have 2g, you have b, which is the known width of the weir. Therefore you can calculate a CD. So remember, after obtaining the data, after obtaining your flow rates, after obtaining your H's, you can calculate the CD that will work for this weir. So a little bit about the experimental setup of the discharge over weirs. Like I said, this is the open channel flow apparatus. This is a this is a lateral view of it. So what basically is that what will basically happen is that we will have flow incoming in this direction. The flow will start to fill up, and we will have a velocity and a flow rate in this direction. In here we have the weir, and here we will have our point gauge. In which we will measure the water level head of it, and then when the flow goes through the weir, it will discharge into the hydraulic bench, and then it will continue. It will recirculate. So we have a plan view also of this. We have the flow going from right to left, and we have the weir in here, and here we have located the point gauge. I don't want to go ahead, but I want to show you how more or less is the hydraulic bench. So as you can see, here is the hydraulic bench, and in here will be our open channel flow apparatus in this position. So we have a pump in here. We have a hose that connects the open channel, and then it will produce a flow, and then it will go back to the hydraulic bench and recirculate. As you can see in here, you have the pump. The flow rate goes up, it goes into the whatever instrument it is, and then it recirculates back to the system. So the apparatus is first leveled and a datum for the hook gauge established. The hook gauge reading is 0. So what basically says that we will have our hydraulic bench here, and then we have basically to level the instrument to 0 degrees to have a better measurements. So that could be in the discussion. One part of the calibration of the system is that we need to level the open channel flow apparatus. Then a series of measurements of discharge and head on the weirs are then taken. And then once the instrument is calibrated, we can start taking measurements at a certain flow rate. The width of the rectangular notch and the angle of the V notch should be recorded, as well as temperature, as always. So like I said, we will be using a width of 30 millimeters for the rectangular weir, and we will be using a 90 degrees V notch weir. This data is, I explained them in the experiment videos. So the width of the rectangular notch, as I said, and the angle are known values. The temperature also. Then, by turning a knot at the top of the tube, the point gauge might be raised or lowered. Its elevation at any time being read off at the scale and markings on the knot. A series of measurements of discharge and head on the weirs are then taken. That is to say that we have our point gauge in here with a needle at the end, and then we can touch a knot in here, and then we can move it like downwards or upward. So we will be able to move at whatever head of the water is in order to take our measurement. Then the point gauge is best set in the surface by viewing it from below, so that its image might be seen internally reflected in the water surface. A series of measurements of discharge and head on the weir are then taken. That is to say that when you have a perfect mirror image of the pin, it should be just touching the water surface. So this is a close-up of the water pin right now. We can see that we have our tank filled with water, and we have either one of these two situations. When our weir is placed, and when the water is just at the base of the weir, you can see it in here. So that would be it. And you can see the pin in here. That will be our first base measurement we will take. So once we have this, then we will produce once we have this, we have to take our measurement. So you can see here that we have almost a perfect mirror view of the pin to the water. So that is what the slide refers to. So we will have this, and we will take the measurement. You see the gauge here with the millimeter resolution indicator. So we will take whatever measurement it gives us, and then we will create a flow rate, and we will make the weir work. So we can see here that we have an H here, a given delta H. So since we have already our base H, we can then calculate our H doing the same but with flow. So this is what it refers when you get a perfect mirror image of the pin. It should be just touching the water surface. And with a little bit of practice, successive readings of a steady level, it might be repeated to an accuracy of 0.05 millimeters. So that means that if you practice a little bit, or if you keep taking measurements and measurements and measurements, your accuracy will be extremely high. Yeah, here we have the way how we take a measurement in these two cases. So we will take one measurement of this that will work as our old measurement, and then we can calculate an H for different flow rates in order to build our curve. So the table of how we will do our experiments will be like this. So for example, for the rectangular weir, we will have 5 measurements of flow rate. So we will have to set our hydraulic bench into 5 times with different flow rates in order to calculate a different H. So then we have our gauge reading, which will be the H, which will be the H at a certain flow rate. So here is not in the table our base gauge reading, which is for the rectangular will be in this case. So for example, if we have a reading of 140 millimeters, then we will use these 100 millimeters for all these readings. So we have then a reading with flow rate. We get this data, and the head will be this data, the base minus the gauge reading. Then we have a mass of water. Then we have time, and this is in order to calculate the flow rate in the experiment. I will explain a little bit further, but these are the data you will need to obtain in the experiment in order to calculate with the equations. And then we will have a flow rate from the mass and time. And like I said before, in order to find CD, we can then plot this Q, and then we can plot this head into log Q and log H to find our CD. So I am going to explain right now what this mass of water and time means in order to calculate the flow rate. For the same way, we have the exactly same table for the B-notch weir. The same gauge reading, head in millimeters, the mass of water in kilograms, time in seconds, flow rate in cubic meters per second. Remember, don't forget to change the units from millimeters to meters to cubic meters, or from kilograms also to cubic meters. Then we have our log Q and our log H. So a little bit of the discussions of results in here. Actually, let me explain you right now how to get our time and how to get a flow rate right now before the discussion. So you can see here that we have our hydraulic bench. We have our hydraulic bench in here. So our open channel flow apparatus will be located at the top of the hydraulic bench. Here we have our known weight, as you can see here. Here we have our known weight, and the way how we calculate the velocity is, the flow rate is that we have a known weight, and also we will calculate a time, and we will therefore with a weight and a time we can calculate our flow rate. So the hydraulic bench is supported as you can see here, by an internal tank. It's supported by an internal tank in which it calculate in which it will calculate a certain volume to get the flow rate. So to explain myself a little bit better, water is going into the system, into the tank of the hydraulic bench, and we have a known weight. So this weight and this tank are connected with a lever and with a pivot. So when the water reaches a certain weight, which is this weight, we have a plug in here, and the tank and the plug will open. So for example, we have a weight of 12 kilograms. So when this part of the system or the tank itself reaches 12 kilograms, the plug will open and the water will start draining. So that is when we have to that is when we have to stop our watch, or when the plug opens, it means that it reached the weight, and then we can calculate a flow rate. So what we have to do is, in this picture we have the mechanics of our weight, the mechanics of our lever, and the pivot. We have also the internal tank. To have a better picture, I also explained this part in the experiment video, so if you are a little bit unsure of how this works, the experiment videos also are there for your help. So like I said, we have a lever and we have a pivot. So we have a known weight, and then we want to know the weight of the water under a certain time in order to calculate a flow rate. So how this works is that first we need to push the lever down in order to, we need to push the lever up where the weight is in order to open the plug. So we have to empty the weight tank by lifting the lever arms to its highest position. So we have to lift this up and let all the water go down. So when we don't have water in here, we have to release the bucket to its lowest position, so as to close and start recording time. So we in this A, we have to hold it to the highest in order to let the water drain. It takes more or less about 35 to 45 seconds. So when that happens, and when we hear that it is completely empty, we just let the lever go and it will go like this. So we just let go and start our time right away. So when we let go, the plug will close and then water will start filling. So we started recording time, and when it actually goes down because we have a weight, so this part is heavy because it's empty. So when it starts filling up and filling up and filling up, then when it reaches a certain weight, which is this weight, the lever will go up again, because these two weights are the same. So when it goes up again it will go up again actually very abruptly. So when it goes up again for the second time, we stop our time. So we have, for example, we are like 20 seconds and we are, the weight is still down. So when it go up one time, it will go up very abruptly, and then it will go down again, and then it will go up again. At the second time that goes up, we will have to stop our time. Therefore, we know a time in which water filled in here, and we know a known weight. Therefore, we can calculate our flow rate. It's very important to say that the pivot is located at 1/3 of the tank. It means that for one here located, we have 3 in this side. That is to say that we have to multiply our weight by 3 because we have an arm of 3. So this will be way heavier than here. So if we have 4 kilograms in here, we have to multiply by 3, and then we will have a total weight of 12 kilograms. This is the 12 kilograms we need to use in our experiment. Like I said, the pivot is located at 1/3 closer to the internal tank, and then we will have to and then the weight will have an arm of 3, in which we have to multiply that weight, the real weight, which is 4 kilograms. We need to multiply by 3, and then therefore we will have the 12 kilograms. So that is basically how you calculate the velocity. That is how you calculate the flow rate. We will have to find a known. We have to find a time in which a known volume or a known weight fills up. So it's basically how fast does the flow rate fills up the tank. That's how we calculate a flow rate. So going back to the table, then we have a known mass. In this case will be 12 kilograms, and we will have a time, and then we can calculate an experimental flow rate. Then we can calculate the log Q and the log H in order to calculate a CD. So the discussions for the results, it could be: the results show that the discharge over the rectangular weir might be represented by the equation in this one. So we calculated the experimental flow rate, but after obtaining a CD, we can also calculate the real one. That is not mandatory, but it could be a nice discussion to do it for the expression of. So you can say the expression, this expression which appears in the equation is the theoretical discharge, not the actual, because as stated earlier, energy losses are neglected. So this is the real flow rate with the CD, and then since before we just calculated with this part of the equation, then we can calculate it again, and then we can obtain and analyze them together. But like I said, that will go to the discussions. The CD is the experimental that you need to do obtaining from the data given. Also, the discharge over the V-notch weir can be represented by the equation, again the other equation that we already discussed, and CD again accounts for the energy loss. CD might differ depending on the manner in which you determine its value by use of graphing, that is the one we will do, the graphing, or comparison of the Q of the flow rate of the actual flow rate to the theoretical flow rate. So we will do a combination of both, because we will calculate from the experimental flow rate. Like I said, the CDs varies. The CD in the V-notch weir will be different than the CD in the rectangular weir. That is because the cross-section area of those weirs are different. So the losses, the energy loss will be different. So it will be a little bit different. So you will have to notice that they are not the same CD for the same shape. And also, if we have a trapezoidal weir, that CD will be also different than these two. And some questions for further discussion, it could be: what suggestions have you for improving the apparatus, thus increasing the CD? Be specific and thorough. So we can say also, we discussed about the calibration of the open channel flow apparatus. It has to be leveled. Also, accounting for the less amount of energy loss. For example, in here, since the weir are not perfectly sealed, when you watch the videos, you will be able to see that when we have water in the upstream, there is a little bit of leakage towards the weir. It's extremely small, it will be negligible, but that is the energy losses the CD accounts for. So, and a recommendation should be that we should seal the weir in a better way. That is to try to eliminate our errors the most as possible. Did you graphically derive CD value match that determined by the given equations? We have to explain. We can explain how did we get. Remember how did we get this equation from the logs, and we calculated and we obtained the CD graphically. And why was one weir design more efficient than the other? Give detailed reasoning and back all the statements with your data. If we have a higher CD, for example, our rectangular CD was 0.6 and our B-notch CD was 0.8, it means that the B-notch CD will work better because it has less energy loss. That is to say that you can compare both CDs to each other and say which option of weir is better for the experiment or to have a real life situation. Usually the CDs are less than 1, because if it's 1, it's completely it will mean that there is no loss. So the CD value is always less than 1. So that is about the discussion. I'm sorry I took a little bit longer in order to explain this. And if you have any question about the further discussion of how to present your results, please let me know. Shoot me an email or schedule a Zoom meeting. I will be available during my office hours or during class time as well. As always, as I said, we have this recorded lecture. We will have the videos of the experiment. I'm sorry about the videos are a little bit like shaky. It's because I really wanted to show you the instruments from all angles, so I am moving around taking the videos and trying my and explaining all the components of the hydraulic bench and all the components of the open channel apparatus. So you have those videos, you have these recorded lectures. These slides also will be available for future reference. You have also the fluid mechanics lab, and you will as well have the group data sheet in order for you to work in this report. Also, this report is due to 2 weeks after today, so you will have, as always, 2 weeks in order to finish this report. Please let me know if you have any questions. Thank you.